Folks, yeah, welcome back to our electronic circuits theoretical concepts. And in this session today, I'm going to just deal about resistive circuits part one. And in this part one, I'm just going to talk about like basic analysis techniques. Okay, so we'll just skim through the basic analysis techniques. Then slowly we'll go to the advanced techniques. All right. So for basic analysis. Uh, the techniques that I will show will just be I will try to solve the exercises, right? So I will just skim through the exercises, give you the ideas, okay, the practical ideas, I mean, with the appropriate examples and the exercises. All right. So let's begin our exercise number one for today. Then if you here in exercise number one, what you have to do is like compute just the resistance of this particular circuit uh, within the terminal. So that means you guys have to see from this side, from this terminal, and just find out the equivalent resistance. And the basic technique is alright, like always, as we have to check out that there is always a series or parallel, right? So always, whenever you see the circuits like this, always this circuits must be seen in the basis of their respective parallel or series situations. All right. So if you check out here, having the common node, okay, in both sides you can see that this is parallel, whereas the another one having only one common node is like called series, right? So for this way, and you guys already know, I think, like there is a special particular rule for calculating equivalent resistance for parallel circuits. So here you have for having two circuits, like I mean two resistor R1 and R2, the parallel will be equals to R1 times R2 by R1 plus R2. Alright, so similar techniques will be used here. Then this circuit, this will, R equivalent will be added with this one, and lastly you will get you add on this resistor, and overall you just get the R equivalent of the overall circuits from this terminal. Alright, and some basic concept you guys have to understand is you guys are just folding it backwards, okay, from back to the, so if you see, this is our front part, okay, so we start folding from the behind, okay, we fold this one first, and then again we fold it with this one, and lastly we fold it, so it's like a folding a paper. Okay, the trick used is like folding a paper situations. Alright, and second thing you guys have to understand is like do not fold from the front terminal. Alright, so it must always fold from the behind, and that's it, and just try to simplify it. And while simplifying to solve this particular circuit, what we do is we just can check out that this is in parallel, so we fold them. That means we find the R equivalent for this particular resistor combination, and then we fold it with this one because it's in series. Then after getting the combination of this parallel and series, we just folded this, the total resistance of this one with this another one, okay, resistor, and lastly we get the terminal, like the overall resistance of the terminal. Okay, so here the solution is stated, that is you get 2 ohm. And like, okay, let's begin for exercise number 2 then. In exercise number 2, what you guys have to do is just like it's the similar concept. Alright, first, whenever you see such kind of circuits, you have to always, okay, see it from the, like try to find out the appropriate situations. Like situations means like where can you find the parallel situation, okay, this, or where can you find the series situation. So whenever, so it's like you are trying to simplify okay, the circuit into a very simple circuit, so that you can you do not have to worry a lot, right? Because this is a very complex circuit, and the basic trick is just to simplify it. And the simplifying techniques we use is just like simplifying the parallel circuits, like parallel resistors with its respective the R equivalent. We find the R equivalent of the parallel. Then similarly we add it with the series. Okay, and then it goes on. And for this one, what we have to do is we can see that this is parallel, so we just find the R equivalent of this parallel. Then we see that this is series with this resistor, so we just add it with this resistor. So combine getting this the R equivalent of these three resistors, we add it with this resistor, and lastly the overall result of this will be added with the parallel with this resistor, and lastly the overall R equivalent of this resistor will be found, and this resistor will be in addition with this resistor, and lastly you will get the R equivalent of overall this whole resistor, and then this will be in parallel with this resistor, which is parallel to our terminal, right? And lastly we find our total R equivalent, right? Then this is the same technique that's used here, and we have the solution for I strongly suggest you guys to just try to solve it out and try to carry it out. Yeah. So what about okay, now let's see exercise number 3 then. In exercise number 3 you just have to complete similarly the terminal R equivalent resistance, and in this situation the circuit is in such a format. So how can we find out? Okay, so always first we have to check out for if there are any kind of parallel or series resistor, okay, series combination. Okay, so we cannot see any kind of parallel or series combination, right, for this kind of complex circuit. So but we can see one combination, that is this short circuit, alright, from C, D, E, F. So whenever you find a short circuit, you have to always be careful in this situation, because a short circuit in parallel with another resistor is going to nullify the resistor. Okay, so what do you mean by nullify the resistors? Means that no current will be flowing from this resistor, this particular resistor. So this resistor will have no voltage, alright, and it's nullified, alright. So also particularly this resistor is in parallel with this resistor, right? Also you can check out R3 is in parallel with this short circuit. So overall this short circuit is going to just nullify three resistors, that are R4, R2 and R3, and we will just get R equivalent that is equal to R1. Alright, and I am using the same technique. I have displayed here how I am using the technique here. Okay, the step 1, you just see the short circuit here, and for step 2 replace the circuit with a short circuit, and then lastly we just get the R equivalent equals to just R1. Alright, for exercise number 4 we have another circuit situation here, and in this circuit situation, so guys, first thing, how can we just find the terminal resistor then? That the terminal is from A to B, so looking from the terminal, in the direction of the terminal, we cannot see any kind of combinations, right? Any kind of combination of this kind of situation of parallel and series. But what I strongly suggest for you guys is just always when you find such kind of complex circuits, you guys have to always be careful about drawing, always redraw the circuit in a simplistic form, so you guys can find out or use your own imagination to redraw the circuit. Imagination in the sense like, for example, you guys can for example, let me show you my imagination of drawing the circuit. What I can do is I can simplify the circuit by redrawing the circuit, saying that from terminal A and between terminal B I can redraw R1, I can redraw like this, and then what I can do is like I can also check out that this R4 is in parallel with R3 because it has this third circuit as a common node and another common node is here, right? So you will be drawing R4 parallel R3, okay? And lastly, the R2 has only one common node, that is this common node with R4 parallel R3, so this will be in series with R2, right? So similarly I can redraw this circuit and I can solve it in a very easy format, right? Whenever you find such kind of complex circuits. And a similar technique I have been using here in this solution. As I have told you, I have just redrawn the circuit, the parallel part, the series part, and again the common part between terminal A and B, and that's it. And after simplifying or redrawing the circuit, the calculation becomes very easy, and I just have stated the total calculation here, and I got the result 8 ohm, right? Okay, so after this exercise, okay, let's begin exercise 5 then. In exercise number 5, for the terminal resistor, that is from terminal A to B, what can be done is first thing is always to try to simplify. Simplify means the technique that we use is always finding the R equivalent of parallel or any combination. Finding the combination first using the respective formula of finding the R equivalent of the combination, and then lastly we just sum or add it, right? And for this one it's just parallel, so just replace with the R equivalent of parallel. Also similarly for this one, replace with R equivalent of parallel, and lastly this whole summation will be replaced with the R equivalent of whole summation will be replaced with the this one plus this one will replace the whole R equivalent, and lastly it will be parallel with this resistor, and then it will be added with this resistor because in series, okay. And this was for the right part, okay, right hand side of the circuit. But when you check out the left hand side of the circuit, you will see that these two are in series but is in parallel with this one. So similarly you find for this one, and will be added with this one because in series with this resistor. So similarly we just try to parallel the left part of the circuit and the right part of the circuit, and lastly we get the overall R equivalent of the terminals, right? And I have used the similar techniques here, and also the solution is presented here. You guys can check it out, try out what I say, use the techniques, okay, that I have given, and that's it. It's a very fundamental techniques, okay, for circuit analysis. And okay, for exercise number 6, okay, you guys are given some values for the generator, that is ET. And the circuit is in such a format, but in such a case, so how can we solve it? Okay, always we are just replacing, okay, and making the circuit simpler, right? So here what you are doing is like just replace these two circuits which are in parallel, and just add it with these two another circuits which are in parallel with each other, and they two will form a new R equivalent. And lastly, getting this total R equivalent, we will try to use KVL. Okay, so using the KVL means R equivalent is here, ET will be here, and the respective 5 ohm is here. So what can be done? The thing that can be done is you guys can just the whole Also this you can replace this circuit. Okay, I'll take the whole R equivalent because this will be in one R equivalent will be added with this resistor, and then the total voltage of this whole resistor, R equivalent resistor, and this one um, will be same. And lastly you do the voltage division, and you just find this voltage division in the sense like you will do voltage division with respect to this resistor and this resistor. Alright, and you find this particular resistor. And what I have done here is I found RAB here. I have to find RAB here. So I found RAB here, and then consequently the current circulated through the resistor is given by, okay, so there are multiple tricks or techniques you guys can use to solve a particular circuit. Alright, it's not like you guys have to follow only one tricks or technique. So here what I have done is like I have just taken R2 parallel R3. So R2 parallel R3, as I have told you, R4 parallel R3, and R1 is added. So total R equivalent is taken, as I have told you before, right? And lastly, we found the current that was like the total R equivalent, and like as you know that the voltage will be same. This voltage will be same with this respective R equivalent, right? And when the respective R equivalent of all the circuits, all these resistors will be equal to the voltage, then you find the current, and respectively after finding the current, you guys can just substitute the current with this particular resistor, okay, and you find the voltage, and as it has been done here. Alright, so now let's begin exercise number 7. So here also you guys have to just compute equivalent resistor A and B between terminal A and B. So what can be done here? Here I have a very particular situation, that is I have three, like the terminals are in a delta form, right? So here we have to use a special technique or tricks that is called Y delta. And for your kind information, Y delta, there is a special formula for Y delta, and I will state it. And Y delta is a certain combination of a circuit in which a circuit will have a resistors in a delta form. Okay, they are in combination of delta form, and you guys can just convert from this delta to Y, that is starting from A. Okay, you can draw a resistor, and there will be a common node, and having common node starting from side B, side from this another triangular point, you guys can draw another resistor. Okay, it will be, the resistor will be in form Y form. Okay, and the formula for the conversion is like this, and the conversion is 3Y is equal to 1 delta. Okay, for resistor. So 3 times delta R resistor, delta Y resistor, no, 3 times Y resistor. Okay, is equals to 1 delta resistor. Alright, so and also be careful that these resistors must have the same value. Okay, and only you can use the delta Y delta conversion. If they are not of equal quantity, then they cannot be converted. Alright, so by these similar techniques I have been using. I will use the Y delta conversion, and then particularly I'll solve this circuit. Okay, similarly I use the Y delta for here, Y delta for this delta. Firstly I use for Y delta for here, then I use Y delta for here. Okay, and then after using Y delta for here, I will just respectively find the combination of series and parallel, and then I will respectively fold the resistors, right, as I have shown the technique before. But guys, be careful that this part of delta you cannot do the conversion of Y delta, alright, because the resistors do not have the same value or same quantity. And I have shown here in a figure. Yeah, look, it will be this delta is converted in Y form or T form. Alright, because if you check out from this angle, it will be T form or a Y form. You guys can see in any form. Alright, and similarly the combination is got here, and lastly we get the combination of parallel here, because we'll add these 2 resistors, then we'll add these 3 resistors, then this will be parallel with this one. That means DE resistors from all these 3 resistors combination will be parallel with this one, and lastly it will be added with this respective resistor. Alright, and that's it. I have shown here also the corresponding solution for this exercise. Okay, now let's begin the exercise number 8 then. Also for exercise number 8, it has already given here a Y form. Okay, so here what you have to do is just to convert it from Y back to delta. And if you convert from Y, this Y to back to delta, it will always again form another delta with the respective values, and it will be parallel with this side will be parallel with this another resistor, and similarly with this one, and similarly with this, another one with this one, and another one with this one, right? And alright, and also I have shown here the particular figure which will describe the transformation, okay, on the ABDC, right? ABDC, right? And ABFE, FE. So, and this is the circuit origin. Then this is just transformed into a delta. Okay, star delta, or you can also say Y delta. Alright, and you guys can also see the simplification of the circuit here. And this is going to be parallel with this. And respectively, we solve all. And this is the particle tricks. Alright, guys, and now let's start exercise number 9. In exercise number 9, what you guys have to do is just to find current I, okay, and that is passing through here. So what can be done in such a circuit? Okay, let's investigate, okay, and let's see what can be done. We can see that there is a resistor here which is in parallel with this combination. Alright, and you guys can also see that there is a specific combination. Okay, this combination is something like a Y, you can see, or because you have a common node here. And let's first find out the value of R6, R7, R8. Yeah, the value of R6, R7, R8 is 10. So this can be converted back, right? Because this has the same value. Alright, so this can be converted back to delta, and after conversion it will form a parallel with here R4, a parallel with R5, and similarly a parallel with both R4 and R5. So it will be a node junction here. Alright, and those parallel will be converted back to R equivalent, and similarly with this one will be converted back to R equivalent, and this the third one will be parallel with R9, and similarly you solve the situation here. And after solving all the situations, after simplifying this part of circuit, we might get something something different, okay, such as like maybe some simplistic, like we'll get one resistor here, or we'll get a yeah, after simplification we'll get just again another Y, which will be in series with R1, R2 and R3 respectively, and similarly we add, and then after addition we'll try to solve for particular value I. Alright, okay, let me show you by the figure then. First, this circuit indication of the nodes. Okay, as I have told you guys, like this is converted back to delta, right? If you guys check out this situation, and then you find the respective, you solve the respective circuits for parallel, this parallel, this parallel, and then add it with the series, and again the parallel is done here. Alright, in the third step, what you guys do is you don't again get a similar combination, that is this one, but both has a common, that is this resistor, that is Rn, and both are equal, so we can convert them back to Y. This is a delta form. If you guys check out, it will be in a delta form, because if you check out the nodes or something like this here, and if it's a node, you guys have to just imagine, okay? You guys have to always imagine while solving circuits, and you have to draw a picture, okay, of the circuits and the formation, because it can have different form, and it's just like trying to confuse you with the situation. So always try to imagine, okay, and try to explicitly figure it out, the combination. And I figure out that this can be converted back to Y, so yeah, I do it here. Then this Y, the part of are in series, okay, similar, these are in series, these are in series, and lastly I get the combination. Yeah, and now after this you guys have to be careful, because we are finding just this current value, right? So we can also combine it back, combine this part B, F, B, and this time like this part we can combine with this particular resistor, and because they are in parallel. But you guys have to be careful that the current that will be flowing here and the current that will be flowing here, okay, like here, and the current that is passing from here and the current that is passing from here are totally different, because here is a junction here, right? You guys have to be careful about this. So regarding this junction and being like taking care of this junction, you guys have to always find that the current that is passing from here will be the summation of current that is passing from here and the current that is passing from here. So we use KCL here, okay, and respectively after using the KCL you can find the respective current. Okay, the current that is passing from here is not equals to current passing from here and here. So just be careful in this kind of situation. Just always be careful of the junction node. But here the situation is becoming simple because our resistors are same. So this might introduce a concept that whenever the two resistors are equal, then it might have the possibility that this have a common, because the current that is passing from here and the current flow inside the junction F will be equals to current here plus here. But in different cases, this current flowing from this junction will be not equal to this junction. But in this particular case, the resistors are equal, so the current flow will be same here, and this will be just added, that is 2 times I with the negative direction, right? With the direction of this particular direction. Because always you guys have to also be careful about that this is a voltage source. So whenever you have to find the voltage source here, the current will be flowing from the positive direction of a voltage source. That is, the current flow direction will be from up to down, okay, in this voltage source. So when the voltage source is up to down here, and the current flowing from here will be negative. So that means current coming from this and this will be totally negative, the summation of the negative. Alright, and that's it. Okay, I have used a similar technique here to solve.
Yeah, but it's much better than the model.
Alright, and lastly you find the current here, okay, by the current division. Alright, and that's it. So for exercise number 10, what can be done? For exercise number 10, we say that we have to find the unknown voltages and current using dividers. Okay, so here is the concept of dividers now. Okay, and the most important concept you guys have to understand. That is like the concept of dividers is that you guys can divide a current, that is a current source, to the respective resistors in series. This is the theory of current, like voltage dividers. Okay, this like a voltage source can be divided into respective series in resistors, and they have the particular formula for that. And this particular formula states that if you want to find a resistor R1, okay, and if suppose if you see the voltage source which is in parallel with which is in the series with the resistors, n number of series resistors. So the first resistor, to find the voltage of first resistor, is the division of voltage of the voltage source. So how do you divide? You divide by finding the division parameter, and the division parameter will be the resistor, first resistor where you want to find the value divided by the total summation of the series resistors. So it will be the sum of all the resistors, total resistors, the resistor where you want to find the voltage division divided by the total summation of the resistors times the voltage source will give you the voltage division of that particular resistors. Alright, and similarly for current division, the current division are always done in parallel. Alright, because the current flows, same current flows through the series combination, and it also does the same, but you guys have to be always careful about that. We check out for 2 parallel resistors. If you want to find the value for resistor R2, then you have to take with respect to R1. Alright, so R1 by R1 plus R2 into the total current, okay, will be they provided to find the respective current in the particular resistor in parallel. You guys can check out the formula from the web. Okay, now let me solve this exercise. For solving this exercise, what I am using the technique is like I am first dividing, taking this as a whole as a one block and a one equivalent resistor. Okay, I am just seeing this as a series with this one. Okay, and I just divide the voltage from here to here, and I just get the voltage V1 here.
Comment.
Alright, by using a simple voltage division. And then similarly also for voltage 3, what I do is I can do and solve it in multiple ways. Like I can also,
because inside the
I can also,
go to the
if knowing the voltage, total voltage here, I can also find by doing the similar voltage division here in these two resistors. I can say that
Real system.
I can, yeah, similarly by voltage division I can find also the voltage here by doing the voltage inside this block. Because from the first voltage division we found the voltage division of here and respectively here, right? And now knowing the total voltage passing through here, that will be regarded as a voltage source. We will have division inside these two voltages which is in parallel. Or you guys can also, yeah. And the voltage inside a parallel are totally same, so it will be the same voltage that is passing from here and here. So it is just the voltage division accurately divided to 50%. Alright, so guys, like you can check out the solution provided here, and it says that yeah, I want first to find, here I use this different technique, not the technique that I just described you just now, because I just did a current division, and that's the easy technique here, because the current I1 is passed as a source here, which will be divided among these two parallel resistors, R2 and R3, and you find R1.
the system cannot show it because
Alright, you can also do in such a form.
I'm an engineer. Okay, JD. So we know JD, it changed the value. Wait a minute. Change the
Now, okay, so the current is calculated from the equivalent resistance seen from the generator. So, what is done here? ES, the voltage source divided by the total R equivalent, that is R1 plus R2 parallel R3, the R1, I1. So, knowing I1, you can know immediately V1, that will be just the product of current into resistor. And for I2, what you guys know is that the current will be divided into I2 and I3, and I2 will be just
wait a minute. See what is without. Okay, so now we know this is
just the current division here, that is for I2, as I have noted you, that you take the current flowing from I2, that is resistor 2, can be found with respect to this formula, that will be the resistor 3 by resistor 2 plus resistor 3, alright, and times the current here, times the current source, and you find the respective current here. Whereas
So,
After knowing the current, we know the voltage here. So after knowing the voltage, you guys can also use the KCL at A. So we can, knowing the voltage, we use the KCL here, and after using the KCL here, we get the same voltage here, right? Because we have just two, like we have a common node, that is this node A and this short circuit, this particular length of a wire circuit. I mean this short
so if you want to cross point
this
Y,
node.
you can
So
easily do it.
this
by
will
changing the
have a similar voltage with this particular
this is
voltage
if you multiply this.
that we obtain after grabbing the I2 current. So similarly you guys can also find the current here after knowing the voltage,
This is basically
or you guys can also use the
this
voltage like KCL here. Knowing this voltage, you can also find the voltage here. I am in the current here. Alright, so that's it. You guys can see the solution here. Okay, as I have already stated in a very systematic order. Okay, I will just leave it in such a way because it's not a very difficult circuit analysis. It's a very simplistic circuit analysis, so I'm just going very fast. Okay. Okay, so let's compute the current. Compute I1, that is this one, using current dividers. And as you guys already know, the current division formula is like current division is done in parallel for resistors that are in parallel. Okay, so using current division we have to find out I1, but before that we also need to find I0, that is I0. Okay, so for that what can be done is like first we have to find out. You can find it in a different form, like you can check out the exercise here. Like it says that current value of I is distributed in I0. Okay, so the value is distributed in the I0 flowing from resistors R6, right? So this current coming from here will be distributed in I0 and R6. So being careful about that situation, what can be done is we found first the R equivalent, like of this one. Alright, that is R3 parallel. R3 is in series with the parallel resistors R1 and R4. Alright, and we find the R equivalent here and this R6 here. And we just use a current division, okay, to find the current for this, that is current I0, that is using this formula, that is R6. That will always, if you need, the point to be noted is like always if you need to find a R equivalent for, or if you need to find the you guys can also always check out this. Okay, this kind of complex situation is only one R equivalent resistor. Alright, and the second point to be noted is like always when for doing current division, you guys have to always use a opposite resistor. Okay, so if you are going to find for particular this resistor the current division for this resistor, then I have to take with respect to this resistor. So R6 is taken here. Okay, but this case is opposite, also different for voltage division. For voltage division, whatever voltage division for whatever particular resistor you want to find, you just take the specific voltage resistor as a value, as a reference. But here I am taking the value of a different resistor.
Now
Okay?
our system, we can say, is
And
good
I have divided it with the total resistor, that is R equivalent
of
plus
mechanical stuff.
this
Mechanically,
resistor of this total
now we need to
resistor
see
of this whole
the
circuit,
effect
right?
of the BID controller.
And similarly with this formula, we find the using this formula we find the total
Okay, I want to do
the
a little trick.
the current division here.
We don't want to work.
And
Work with
after knowing the current here,
to be sure
we can also similarly use the same current division to find the current I1 using the same current divided formula, alright, that I have done here. Okay, so right now
this be really
calculate the voltage, this terminal voltage V1 with voltage dividers.
during the lab.
As I have noted you, or as I have told you before, that voltage dividers are always divided among all the resistors which are in series, right? So here is a different complex combination. So what can be done? So the basic idea is always to simplify the circuit and just
This is magic.
check this circuit as a whole, as a one block. All right. So what I will do here is I will just for this block I will just take, look, as I have done, like I am going to find R equivalent for this whole block. I take it as a whole, as a one R equivalent circuit. Alright, and after taking as a whole block, it will be very simple for me to divide the voltage, because here the voltage will be divided here in resistor R5 and this whole block, okay, using the similar formula. And R equivalent will be found by using the simple technique of series and parallel combinations. Alright, so, and that's a trick it's used everywhere and also here. And for R equivalent, what you find is you find that R6 plus R4 will be parallel with R1 and the respective R equivalent will be found. And lastly, after knowing the R equivalent here, the also voltage will be divided here, so you get voltage 2 here, okay, by using voltage division. And then after knowing the voltage here, this voltage will be again divided with this R6 and R4. Alright, if you can check out, this voltage will be divided also to R6 and R4, and our ultimate goal is to find the voltage V1 that is similar with voltage R4 in this terminal. Alright, and as thus we get the voltage here by voltage division, again by dividing voltage 2, and you get the answer here. And that's the simple trick it's used. Okay, so now there is another complex circuit provided here in exercise number 13, and it says like what, like compute VAB, so AB, terminal AB. So how you guys can check out for terminal AB, what can be done?
Always
Circuit situations, you guys have to always be in, like, creatively, okay, you guys have to redraw the circuit, okay, or you guys have to check it out where the combination exists. Alright, so like our combination, our basic theorem, okay, all the fundamental concept like voltage division, current division, okay, and parallel and series, this fundamental concept must be understood. This is the first step, and the second step is always to find the combination. And if you go check out the combination, what can be seen is like this voltage can be divided into this and this, right, which is in series. If you check out, seeing this as a whole, as a loop, one mesh, Okay, so after checking out this as a one mesh, you guys can find the voltage division. That is, let's find voltage division here. So after finding the voltage division here, you guys can again check out for the mesh of this loop, that's the second loop, and you will find the voltage division here. Alright, that is for this particular resistor. And after knowing the voltage division here and here, you guys can find the voltage division here. That was our goal, and we'll take a case KVL here and find the voltage division. Alright, and that's the trick it's used here. Okay, you guys could use also this. Okay, it's not that I showed you this trick, but here in the solution I am using this trick. Like I'm first finding the voltage division here, then I'm finding voltage division here, then I'm just summing. I'm finding the KCL here. I mean KVL here, right? So also this can be done from both sides, from upper side or lower side. From any side you guys can find the voltage division in this terminal. This is VAB. Okay, so all the solution, okay, with the respective format is provided here. As you can see that VAB. And for your particular information, guys, always be careful. Also, I have noted this concept in my previous lecture. You guys have to always find out, like, whenever you are finding a voltage that is from terminal A to B, you guys have to always be careful about the direction. What is the direction? Okay, so direction will be always from this B, that is the second part, to be towards A. That is the first part. That is the trick. So whenever VAB is given, the direction will be always from B towards A. Okay, so that's the trick. And this trick will be very useful later on in our complex circuit analysis. Okay, that's it. And right now, okay, so now we have a very fundamental and a very new concept, that is superposition. This is a very fundamental concept, and I guess you guys know what is superposition, but if you guys do not know, let me state what is superposition. Superposition is done only in the case if you have multiple generators, alright, or multiple source. So here we have one source, that is E1. Also in this case you have another source. So in one circuit, in one complete circuit, having more than one sources, each source has a contribution towards the respective circuit elements, that is this resistor. So the contribution of each sources will not be missed, or we should not be we should not miss this contribution. Okay, we should not avoid this kind of contribution. So we have to always include this contribution. For this kind of multiple sources case, we have to use superposition theorem. So in this, like, first what you do is you find the contribution of E1 closing the source E2, and second you find the contribution of E2 closing the source E1, and lastly you add both the contribution for each circuit element, and you find the total result. Alright, and this is called superposition theorem, and that we will use here. Similarly, as I have told you, I will just find the contribution of E1 first, closing E2, and with the respective circuit theorems also. Okay, we first find the combination, and the combination that I found is like BC is equal to B, because the nodes are common, right? And we use the divider to find BC. yeah, R3 and R4 will be parallel and voltage division will be done from voltage this one to this voltage, right? And that's it. On secondly, we find the contribution of E2, and for this contribution of E2, you also do the same thing. Just simplify the circuit and just try to divide the voltage. Let's investigate for this exercise then. For this exercise, you guys have to just use this superposition, alright? So superposition is the concept in which the generator, there are multiple generators in a given circuit, so we have to find the contribution of each generator, alright? So that is the theorem of superposition, that states that okay, the contribution of each sources should be calculated, and it will be equal to the value of the corresponding circuit element. So whatever circuit elements, for whatever resistors, whatever circuit elements you want to find, the value will be the summation of the contribution of all the sources present in the circuit. Okay, and with this concept, let's solve this exercise and this circuit. So in this circuit, like, you guys have to first take in, like, with respect to source E1, and you just like neglect other sources, so that means the sources are closed. And the point to be noted is, like, whenever you close voltage source, then it will be replaced by short circuit, alright? So all these voltage sources will be replaced by a short circuit, and after that we will generate a new circuit, okay, that is defined in this exercise. Okay, so you can check out, like, I replace this with a short circuit. I replace all the generators with a short circuit, and this, because this generator is a voltage generator, and then I get a new circuit, and I try to find the contribution of this source, that is E1, to this circuit element, that is I, that I am going to find. And overall, getting this circuit, I just again simplify the circuit with this circuit. Okay, I simplify and get this circuit, and then I try to solve for I, that is current. So, but here also, to solve, I am using a special theorem that is called Millman theorem. And what a Millman theorem states that is, we have always, while we use Millman, we have to be careful about checking out that this is a top node, whereas this is a bottom node. Alright, so Millman always works when we have a top node and a bottom node, and all the circuit elements that are the resistors are in with respect to this top and bottom node. That means with respect means within parallel. So they must have this common top node and bottom node in common. So all the resistors present, okay, all the circuit elements present having common node, okay, top and bottom, can be solved by using Millman theorem. And having the common node, okay, I am solving it by using Millman, and the particular formula is to find the voltage, and for finding the voltage, what we have to find is the total sum of the current, okay, all the sum of the current of all the circuit elements present having the common node will be divided by the total sum of all the conductors, okay, conductance, resistance, conductance, that's the inverse of a resistance, right? So that's it, that's done here. And lastly, we find the voltage here, and after finding the voltage, we can easily find the contribution of I here. right? And similarly you can also have to find the configuration of E2, which will have its own circuit. Then the circuit will be again simplified, then again by using the Millman I find the configuration of source E2, then for ET respectively. Okay, you can check out here. And similarly for lastly for E4, okay, and for in case of E4 there is a big short circuit present here, so the contribution of I1 will be totally neglected here because it's parallel with the short circuit, no current flows here, so it will be 0, right? And lastly I get the final solution here. Alright, so that's it for solving this exercise. Now lastly for this exercise I will is about power dissipation by resistor R2, and I need to find the power dissipated by these resistors, that is R2. And now what can be done here? It says that we have to use superposition for power, and for this particular concept you guys have to first find out for is there any combination that I can just simplify the circuit. Just check it out first that, and this source is in is a common source between this resistor R2, R4 and R1, R3, right, having node common. So our point of consideration is circuit element R2, so I just take the right side of the circuit. Okay, I just ignore this circuit and I try to take a KVL and solve for R2, and using KVL I find the value of R2, which is the contribution of E2, and secondly I also try to find the contribution I that is divided among this one and this one, right? So yeah, that will be divided among this one and this one, while this will be a short circuit, this will be closed. When there is a contribution of E1, this will be open circuit. Also, this is another important point you guys have to understand is whenever you guys have guys want to close a current source, then it is always replaced by a open source. Alright, and whenever you want to close a voltage source, it is replaced by a short circuit. Alright, so that's the way it is used. First, replacing the I with open circuit, I just find the contribution of E1, and secondly I find the contribution of I1, making this short circuit. So having this as a short circuit, and the contribution of I1, I will be something like how can I find I, because having this as a short circuit, okay, it's a very different situation there. It says that you have to just do the current generator. The current generator is there, so it is just divided R4 by R2. So what I am using is I am just dividing the current. Okay, and previously I just did the voltage division, and right now I am just doing the current division, and I am dividing the current here because these both are in parallel. And I just find the contribution of I here. Okay, you guys can, okay, so that's it. But okay, always be careful in case of power. The sum of power contribution, like sum of contribution of voltage, is found here, and respectively for that particular resistor I just replace the voltage in a resistor, particular resistor, that is R1, and thus I try to find the here is the figure, and I try to find the power, right? The loss of power is just the sum of the voltage, that is 8 whole square by the 15, that was the resistor R2. And and also there is another important point that you have to understand is like The principle of superposition do not apply for the calculation of the power. So if you calculate the power sum or power dissipated with the associated individual contribution, it will be incorrect value and disagree the calculation above. So for individual receiver, if you try to find the power dissipation, so for individual sensor that is for voltage 2, voltage 1 that was 16, and with the respective resistor that is R2 that is 15, it was different, right? For similarly for the contribution of second resistor was different. So the sum of the contribution is totally different from this contribution.
This is C.
Right?
And this U10T.49, right?
So the principle of superposition do not apply
This is what they said.
to the calculation of power.
Yeah, this is DC. One is DC.
When you just try to find the power dissipation with the individual contribution, but because previously we used a different trick, that is just find the
Right here.
voltage, total voltage,
Non-linear.
contribution, and then we change the power. Okay, here if you try to use the power, just like power contribution directly, then it will be a very incorrect solution. So always try to first find the voltage and current contribution, and only sum of the voltage and current contribution, and only solve it. Do not try to directly find the power contribution immediately. This will be like a wrong solution. Alright, by this small and important concept, I would like to close this session, and thanks for listening. And